broadly the strain rate of deformation is a function of three factors: stress, temperature and microstructure. Of course, there are some other factors such as elastic modulus etc., but by and large stress, temperature and microstructure are things that you can play around with and to understand how it influences creep deformation. So, now let us look at the case of stress and temperature. So, we looked at effect of stress and temperature on strain rate. So, what is the corresponding effect of stress and temperature on the creep curve itself? So, here we have three creep curves. The first one corresponds to applied stress sigma 1 and test temperature of T 1. The second one corresponds to applied stress sigma 2, temperature T 2, and the third one corresponds to applied stress sigma 3 and temperature T 3. Now, sigma 3 is greater than sigma 2, greater than sigma 1, and T 3 is greater than T 2, greater than T 1. So, what we are clearly seeing is when we are increasing the stress and temperature. So, that this is the direction of increase in stress and temperature. So, there are things, these are the following things that are happening. When you increase the stress and temperature, first thing that we are noticing is an increase in the instantaneous strain epsilon naught. So, the instantaneous strain epsilon naught is also increasing. So, this is corresponding to curve 1, say epsilon dot 1, this is corresponding to curve 2 epsilon dot 2 epsilon naught 2, and this corresponds to epsilon naught 3. So, as you increase the stress and temperature, the instantaneous strain is going to increase. What is also increasing is the slope of this secondary stage or the steady state creep stage. So, the slope is increasing, which means the strain rate of deformation in the secondary creep stage is also increasing. So, if you see the slope is gradually increasing as you go from curve 1 to curve 3. So, the minimum creep rate or the secondary stage creep rate or the steady state creep rate, all three remain the same. So, that value also increases as you increase the strain rate as you increase the temperature and stress. What we also see is the time to failure. So, this corresponds to the time to failure. The cross indicates the point where the sample has failed. The time to failure is also coming down as you increase the stress and temperature. So, these are primarily the three things that would happen when you increase the stress and temperature. You will have an increase in the instantaneous strain, you will increase the steady state creep rate, and you will decrease the time to failure. Now, let us look at the effect of microstructure. Now, effect of microstructure. So, one thing to remember is when you are obtaining creep data in order to predict the life of a material or the life of a component, it is important that the microstructure stays constant. So, creep data is generally analyzed under constant microstructure conditions, and to achieve a constant microstructure during the creep test, the material has to be heat treated or stabilized at a temperature higher than the test temperature. So, say if you are planning to do a creep test at a temperature T 1, then for the microstructure to stay stable during the course of the creep test, the material should have been heat treated or annealed at a temperature T 2, where T 2 is greater than T 1. So, if you do that, for example, if you want to carry out a creep test on a material with a grain size of D 1, now the grain size should have been attained by annealing at a higher temperature. So, you should have, so let us say D, grain size D. So, this D should have been attained by annealing at a temperature T 2, and so that when you do your tests at T 1, the grains do not grow, because as we know, as we increase the temperature, the grains tend to grow. So, your creep test temperature should be lower than the temperature at which you have stabilized your grains. Of course, having said that, one cannot rule out stress assisted microstructural changes, since creep happens under both stress and temperature conditions. So, stress assisted microstructural changes could happen sometimes during creep test, and so what this means is that the effect of the stress has to be understood before assuming that higher temperature annealing has stabilized the microstructure. So, for certain materials stress can lead to microstructural change, for example nanocrystalline materials. So, it is an evolving area of research and development. So, in nanocrystalline materials the grains tend to be unstable, and even though you have stabilized the grains at a higher temperature, but in the presence of a stress sometimes stress assisted grain growth could happen, and hence one needs to be careful while assuming that the grains or the microstructure is stable. So, now what is the effect of microstructure? This part is about stabilizing the microstructure. So, you want to keep the microstructure constant for carrying out your creep tests and analyzing your data. So, what exactly happens when the microstructure is different? So, if you have say a finer grain size or a coarser grain size, how does it affect the creep data? So, with microstructure could mean different things, but primary microstructure descriptor is the grain size. So, it is the most important microstructural parameter. So, now we know we all know very well that the Hall-Page equation describes the dependence of strength on grain size. So, this is the classic Hall-Page equation, which tells that as you reduce the grain size, the strength of the material is going to increase, which means that the material is going to become more resistant to plastic deformation with grain size refinement. So, if the material is going to become stronger and more resistant to plastic deformation, then that would automatically mean that it should also be resistant to creep deformation, because creep is a type of plastic deformation. However, what is very interesting is the Hall-Page equation does not directly work when you are talking about creep deformation conditions. So, this equation fails to explain the kind of behavior the material exhibits during creep conditions. So, what happens is during creep conditions, it has been observed in from a large number of studies that as you refine the grain size, in fact the material is going to creep more. So, the strain rate of deformation, creep deformation is going to increase as you reduce the grain size. And to understand this, I would want to talk about the concept of equicohesive temperature. So, equicohesive temperature is basically a temperature, it is a temperature below which finer grain sized material are stronger and above which finer grain sized material are weaker. That is because at temperature lower than the equicohesive temperature, the grain boundaries tend to be stronger, whereas when you exceed the equicohesive temperature, the grain boundaries become weaker. So, the important thing here is, since creep is a high temperature process, so the temperature is somehow causing the grain boundaries. In the presence of temperature, the grain boundaries which are known to be barriers to plastic deformation actually start helping plastic deformation. So, that is why when you talk of creep deformation at high temperatures, the grain boundaries are not exactly barriers to plastic deformation anymore, and that is why the behavior of a material does not follow the Hall-Page equation when you talk of creep conditions. So, a summary of what I spoke. So, under creep conditions, the material tends to deform more with grain size refinement. Of course, there are certain mechanisms of creep deformation that operate faster in fine grain materials compared to coarse grain materials, especially so at high temperatures and low stresses. So, one of the examples is grain boundary sliding. So, this is a mechanism of creep, and we are going to talk about this mechanism of creep in the coming portions. So, by and large, the relationship between strain rate of deformation, creep deformation and grain size can be given by the following, can be described by the following equation. So, epsilon dot is proportional to d to the power minus p, where d is the grain size and p is the grain size exponent. So, what this means is, when you reduce the grain size, so epsilon dot is 1 by d to the power p. So, when you reduce the grain size, epsilon dot increases when D decreases. The strain rate of deformation increases when the grain size is brought down. So, if we consolidate all of these, so we have looked at basically the effect of stress, we have looked at the effect of temperature, and now we spoke about the effect of grain size. So, all of these have a role to play in the deformation rate. So, if you bring all these information together, in general the strain rate of deformation is related to applied stress, temperature and grain size of the material by the following equation. So, epsilon dot is proportional to d to the power minus p, it is proportional to sigma to the power n, and it is proportional to exponential of minus q over r t. Like I mentioned earlier, p is grain size exponent, n is stress exponent, q is activation energy of deformation, and a is a constant. Now, what people have observed is the values of p, n, q and a vary with the mechanism of deformation. So, if your creep deformation is happening by diffusion of vacancies, then you will have a certain set of values for p, n, q and a, but if your mechanism of deformation is happening by dislocation based mechanism, then you will have a certain different values, certain set of p, n, q and a values. So, what this basically tells us, if you wanted to find out which mechanism of deformation is controlling creep, then what you have to basically do is find out the values of p, n, q and a, and from there you will get insights about which mechanism of deformation is controlling creep. So, that is basically the effect of different factors. Of course, one point to note here is sigma to the power n dependence. If you remember, in the previous slide I was talking about epsilon dot being proportional to some a function like that, but by and large what people have noticed is this is the kind of relation that works, and depending on the value of your applied stress and about depending on the dependence and depending on how nu is related to the applied stress and some other factors, the final equation that people have by and large noticed is of this form. This is the dependence of strain rate over sigma. At very high stresses, this relation also changes, and that is something that I am going to cover in the coming portions. At very high stresses, the dependence of strain rate epsilon dot on sigma can take an exponential form, and this is generally known as the power law breakdown, which will be discussed in the coming section.